Alright, so now we're going to take a look at weak acids and bases. Before we looked at strong acids and bases, we found out they were fairly straightforward because this was a stoichiometric type of reaction. Now we're going to look at weak acids and bases. And remember, when we were talking about weak acids and bases before, we talked about how those are equilibria. Stoichiometric, equilibria. Alright, and so we're going to have to handle these using our tools that we learned for dealing with equilibria and equilibrium situations. So, there are going to be 5 steps that you're going to have to do. These are going to seem very familiar to you because they're the same steps or similar steps to what we use when we're doing straight up equilibrium reactions, not just acid-base. And number 1, we've got to have the appropriate balanced chemical equation for whichever type of reaction we're dealing with, or whether it be an acid type reaction, acidic reaction, or a basic reaction. Then we're going to go through and do the initial change equilibrium, the ice table, just like we had done before. Plug everything into the equilibrium expression from that equilibrium row on the ice table. And then we're going to calculate what that particular change or that x value would be from the ice table. It says use assumption if possible. We're going to find that we can make an assumption. It's going to make the math a whole lot easier for us. But in order to use that assumption, we have to check to see if the assumption is valid. And we're going to talk about how we might be able to do that. So we're going to walk through all the steps. We're going to do this in terms of a problem. So we're going to work a problem 2 different ways to show you that it will give you the same answer, just you doing it just slightly differently. One is going to have an easier or a simpler form of math that goes along with it. And not really form of math, that's not really the way to say it. I just can't think of the word right now, the right word that I want to use. But there are going to be 2 ways we're going to calculate it. Number 1 is going to be like we had to do before, where we pulled out the quadratic equation. We had to put the a, b, and c value from the quadratic equation that we had, and calculate what the root would be. And then you can make an assumption that's going to simplify this calculation. So there's one of those 2 ways that we're going to use. I'm going to tell you that if you can use the assumption, you should always use the assumption. It's going to make your life a whole lot easier. All right. But the thing about it is, in order to use the assumption, you have to specify or show that that assumption is actually valid. So the problem that we're going to look at, and the problem that we're going to do, and I'm going to put the screen up here in a second, is very similar to the one that we saw before when we were dealing with strong acids and bases, where we said, what's the pH of a 0.1 molar hydrochloric acid solution? What's the pH of a 0.1 molar sodium hydroxide solution? What's the pH of a 0.1 molar acetic acid solution? And the key here is acetic acid is not a strong acid. It's not one of that list of 6 strong acids that we learned. And there's a tip-off that it's not a strong acid. The Ka is provided. For a strong acid, the Ka would be as close to infinity as it can be. It's going to be very, very large because those acids are so strong. For a weak acid, it's going to be something else, something significantly lower, but it will be tabulated. You will be able to find it, and it almost always will be given in the problem. So that's going to be your tip-off. But we're going to work this problem, and we're going to do it by following through those steps. Following through those steps that we saw on that previous slide. And number 1 was we have to write the balanced chemical equation for this. So we have acetic acid. It's going to be in equilibrium with H plus and acetate. Acetic acid gives up a proton, becomes acetate. Acid, conjugate base. Alright, so far so good. We've got the balanced chemical equation. Next step, we need to write our ice table. I, C, E, initial change equilibrium. We're starting with 0.1 molar acetic acid and no proton and no acetate. Then we're going to have a change. In other words, we put this acid into the water, into the solution, and nothing happens. That's this point right here. Then we let the reaction go. Some of that acetic acid is going to give up its proton, and so some of it's going to go away. How much? We don't know, because we don't know what the equilibrium concentrations are going to be. So minus X, because it's a 1-to-1 mole ratio, this is going to be plus X and plus X. And so here, for the equilibrium concentration, we have 0.1 minus X, X, and X. So now we know what our equilibrium concentrations are in terms of, or written in terms of X. Now we can write the Ka expression, and this is going to be equal to the concentration of H plus, which is really the thing that we want to determine in this problem, because we want to know the pH. And if we know the concentration of H plus at equilibrium, then we know what the pH will be, or we can calculate. The concentration of acetate all over the equilibrium concentration of the unionized acetic acid. Now we can start plugging stuff in. Ka, 1.8 times 10 to the minus 5th power. Concentration of H plus is X. Concentration of acetate is X. Concentration of acetic acid, 0.1 minus X. Where those all come from the equilibrium row of the chart. Multiply both sides by 0.1 minus X. You get 1.8 times 10 to the minus 6th minus 1.8 times 10 to the minus 5th, and that's times X, and all that is equal to X squared. Now, because we now have a quadratic, we have to get everything in the right form, and remember there is a certain form for a quadratic, so we're going to take everything over to the right hand side, and we're going to get X squared plus 1.8 times 10 to the minus 5th times X minus 1.8 times 10 to the minus 6th, and all of that is equal to 0. So we've got everything set up, right? We've got our A, our B, and our C values. So for the quadratic formula, A is 1, B 1.8 times 10 to the minus 5th, C minus 1.8 times 10 to the minus 6th. And you can plug that all into the quadratic formula, solve for what the roots would be, and it turns out that the root with a value of X is 0.001333 molar. And we know from going back to our ice chart that X is the concentration of H plus at equilibrium, so we can now go and determine what the pH would be. pH is minus log of the concentration of H plus concentration at equilibrium. pH is minus log of 0.001333 molar H plus. Plug that into your calculator, and the pH ends up being 2.87. pH below 7, so it's acidic. All right, so we have an acidic solution, but not nearly as acidic as that strong acid solution of an equal concentration, 0.1 molar. So that's how we get to that point. The big amount of work is right here, okay? So there's a lot of work here. You know, going from that polynomial, from that quadratic equation, down to the root is going to take some time. And it's annoying, and you don't want to do it, and I don't want to do it. Trust me, I didn't solve this when I was working this problem with that quadratic formula. I solved the root some other way because I don't want to do it either. So I want to show you a way that we might be able to get to that point. And to do that, I want you to notice that this change, this X, which is the change in concentration for acetic acid, is really, really small, right? Not much of that acid is dissociating at all. And that's going to be the key to the assumption that we're going to come up with. All right, so I'm going to pull this back down. All right, so we had two choices, right? Number one, quadratic formula. You get a quadratic, you got to solve what the roots are. Or number two, we can simplify the calculation with an assumption. And that's what we want to do, is we want to understand or learn what that assumption might be so that we can go through and we can do and solve those problems a little more simply. So, the key to this, like I said and I showed you in that last problem, the key is that change as we go to equilibrium from the initial to the equilibrium concentration is very small. All right, that number that we calculated was very small compared to 0.1 molar. So only a small portion of that acid is giving up its proton. Now, we're talking about this in terms of a weak acid, but this is going to be the same for a weak base. We're going to see, I'm going to solve a problem in another video coming up with a weak base. We're going to be able to do the same thing here. All right? So what we're going to do is we're going to take this fact that is not ionizing to a very large extent and use that to our advantage. All right? So how do we work through this? Well, let's go back. And what we're going to do is we don't have to redo this entire problem. So what I mean by that is some of this stuff, let's just get rid of it because we're going to have to redo the pH anyway. We're going to have to get all to here, but you know, the place where the assumption is going to come into play is going to be right here. So we said that X value is very small compared to the 0.1 molar. So that change is very small. So essentially, if you take a big number and you subtract a very small number from it, okay? A big number with a small number subtracted from it will essentially give you that big number right back. So when you take 0.1 and subtract something really, really small from it, it's essentially still going to be 0.1. And so what that means is we can make the assumption that X is much, much smaller than 0.1 molar. And when we do that, that X on the bottom in the denominator goes away. So we can rewrite this as 1.8 times 10 to the minus fifth is equal to X times X, or X squared, over 0.1. And when we do that, this becomes so much easier to solve. Because let's go through. Multiply both sides by 0.1. We get 1.8 times 10 to the minus sixth equals X squared. Now what do we have to do? If we want to solve for X, we take the square root of both sides. Okay? We want to take the square root of both sides. So we're going to end up with 0.001342 equals X. No quadratic formula. We don't have to solve for any root of a quadratic equation. We just take the square root of both sides. And that makes this problem so much slicker. Now the thing is, this only works if we come back and take this value and we put it in and determine the pH and it gives us the same pH. And there's even going to be a second check that I'm going to make you do to make sure that this works. And that assumption right here is valid. Okay? And that is, let's take this forward and say, okay, so X is equal to the concentration of H plus, and that's equal at equilibrium, 0.001342 molar. And then we're going to say the pH is the minus log of the concentration of H plus, 0.001342 molar. And then the pH of that solution would be 2.87. Does that look familiar? That's the same thing that we got going through the whole long process with the quadratic formula. So why would we ever use a quadratic formula with an acid-base problem if we don't have to? Now the key is, the question is, can we just use that assumption, or do we have to use a quadratic formula? Now, it's a pretty good sign in this case that both ways gave us the same answer. We now have to go through and show that it actually makes sense that we have done this, that assumption is valid. All right? Because normally if you're working through a problem, you're not going to do it both ways. You're going to do it one way. You're going to do it with the assumption that's going to make your life a whole lot easier, and then you're going to say, okay, this is the answer. But that's not, you have to have some way to show, okay, well, the assumption that I made in that case actually is reasonable. All right? And so to do that, we're going to look at something called percent ionization. And it turns out that assumption will work if the percent ionization of an acid is below 5%. So we now have to check to see whether the assumption that we just made is a valid assumption to have made. So we're going to use this percent ionization, and we're going to be able to write this for an acid or a base. You're going to notice right away this should be H3O plus. All right, I forgot the plus sign in that equation. But we have two, one for an acid, one for a base. For the percent ionization for a weak acid, it's going to be the equilibrium concentration of H plus or H3O plus divided by the initial concentration of the acid times 100%. Or we're going to calculate for a weak base the concentration of hydroxide that's produced by that base over the initial concentration of the base times 100%. If that percent ionization is less than 5%, the assumption that you make to do that problem is valid. Now I'm going to tell you, you're probably saying to yourself, well, what if I'm on a quiz, or we're taking a quiz or an exam, and I do this problem, and I find out the assumption isn't valid? Do I have to go back and do the problem the long way? And the answer is no. All right? I would want you to state that that's the case. I would want you to say, look, I made the assumption in solving this problem, but the assumption is not valid to make in this particular case. That will be good enough for me. So that means you're really only going to have to solve acid-base equilibrium problems using the assumption. All right? Which is really, really kind of nice. Unless I tell you, don't make the assumption for a particular problem. But I'm going to be honest, that's something that I would do if you were in the classroom and you were here and we could work together. I'm not so sure that's something that I would do as we're trying to learn this, across distance in the way that we are, or learn it remotely. So that may give you a hint as to what type of problems ways you're going to have to solve these problems. All right, so let's go back. Let me erase what I can erase here and leave some of the other stuff. All right, so if we want to determine what the percent ionization would be for the acetic acid in this problem, we would say the percent ionization, I'm going to call it percent I. Why? Because I'm lazy and I don't want to write out percent ionization. It's going to be the concentration of H3O or H plus 0.001342. That comes from solving that expression, or taking the square root of both sides, and that's molarity, all over the initial concentration of the acid, and the initial concentration of the acid is 0.1 molar. And if you solve that, you end up determining that that acid is 1.32% ionized. That means only 1.32% of all of the acetic acid molecules have given up a proton. Like 98.7% of them still have their proton. All right? Only 1.32 give or donate their proton. That is much, much less, or less than 5%. So then we would say the assumption is valid. And if the assumption is valid, then we just leave it as it is. We have solved the problem the way we have. If the assumption was not valid, I would want you to put down a statement to say the appropriate way would be to go through and solve the expression using the quadratic formula. So that's it. That's how we deal with weak acids and weak bases. I'm going to record another video showing how to work through a weak base, because there are some slightly different things. In particular, writing the balanced chemical equation for the base is a little bit trickier. So I want you to take a look at that as well. Now we know how to calculate the pH of a solution of weak acid or a weak base.